Hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and I like to bring you behind the scenes to talk to some of the researchers who are working on the concepts that we talk about all the time. And today, I am delighted to be joined by Dr. Jonathan Jiang, who comes from NASA JPL. Welcome.
Okay, thank you. Yes.
So who are you? What do you do?
Well, I'm a scientist at JPL, and I'm actually talking to you. I cannot represent JPL. I just represent myself. And
Sure, no problem.
and
We
are
if JPL's
doing,
listening, it's just me and Jonathan,
right.
just
Yes, yeah.
over a beer,
Okay.
talking about crazy ideas.
Sure, yes.
Yeah.
And I'm actually a manager in a group. And, because the Earth observing satellite, we have two satellites in orbit. One is observe the cloud. Another is observe the aerosols. Aerosol is a pollution on the surface. And so that's we do. And every day at JPL, actually, we are doing something called end-to-end. And so we design the satellite, and our contractor launched the satellite, then we analyze the data.
And so which are the satellites that you're working with?
Okay, and the one is called MISR. It's called multi-angle imager for aerosol studies. Another is called CloudSat. A CloudSat is to observe the cloud. And so there's the scientist and in my group is working for these two satellites. Yeah.
Right. And so like that's your day job, but you can't resist working on a whole bunch of other papers. I mean, you have when I last checked, you have 220 papers that you've contributed on.
Right.
And you spend a lot of time thinking not only about aerosols and the methods of detecting them,
Right.
but more philosophical concepts like why are we seem to be alone in the universe, and what does the future hold for human space exploration? So there's sort of there's like three papers, fairly recent papers that I think are really interesting. But the one that you worked on that I saw just a couple of days ago was getting a sense of what the future of human space exploration looks like across the solar system. And you've gone way beyond the moon and Mars to think about what the future really, really holds. Why did you work on this? What was the idea for this paper? What caused you to talk about this?
Okay, so this is a very interesting subject. And a little bit more than 2 years ago, Steve Hawking passed away. Okay, and 2019. And Steve Hawking visited Pasadena quite a few times. In one of the talk, he think, and humanity cannot live forever. And for some reason, he believed we only have about 1,000 years left, maybe only 200. Why? If you look around, and there's a lot of problems facing us, and people talk about the great filters. And there are lots of people think the great filter is before us, it's not behind us yet. Now, and there's a Fermi paradox. Okay, there's 400 billion stars and in the galaxy, trillions of galaxies in the universe. Why not nobody visit us? So a little bit more than a year ago, and I and my colleagues published a paper. We did a simulation to see, hey, and not only the question how many civilizations in the galaxy, but how long they can survive. Okay, so there's many factors limit us. For example, and the sun cannot live forever. Okay, there's a supernova explosions. If you're too close, and it's in danger. Maybe asteroid hitting the Earth. Okay, maybe the climate change. Okay, but many factors, happens in a long time scale. For example, in 1 billion years, maybe our sun is become too hot. And but in the computer simulation, we discover one thing which is astronomy. It's called the self-destruction rate. If we play the equations, we know the density of the stars, we know their evolutional time scales and things like that. So we know the life may take billions of years to appear. There's evolution of human life, things like that. But if the self-destruction rate, let's say 0.001%, okay, 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 0. is dangerous to us. If you check the internet, say doomsday clock, you are fine. Wow, and the chances to have a nuclear war every year is about 0.27%. And now, and so this is dangerous. So in the computer simulation, we identify the most impactful factor, limit the lifetime of civilization, and its self-destruction rate. If the self-destruction rate says 0.1%, then perhaps in the galaxy, nobody's older than us. So that's the Fermi paradox. You think about ourselves. We are smart. We have a modern technology. We have physics. But we are not able to travel to the stars to visit another civilizations. Why? And we are trapped on this tiny rock with limited resources. Maybe in 200 years, there's another Einstein discovered new physics. Okay, we can travel to stars through the wormholes, or we develop modern technology, we do that. But can we survive that long? We don't know yet. So that is the triggering question, forced me to think, okay, Steve Hawking said we have 200 years left. But in order to survive, we need to move, maybe migrate and outside the Earth. But can we do that? If we do that, how long it's going to take to us and to do that? It is very difficult to estimate, but we can use the historical data, the speed of technology advancement, and the speed of economical development. Things like that, we can try to estimate when we can, and to do that. So this is all the motivation behind. And fortunately, when I talk to my colleagues and, talk to my community, attending international conference, many people interested. So, so we work together and to come up with these papers.
Right. And it's interesting that sort of line of thinking follows a similar, like when you think about, say, when will humanity become a Kardashev 1 civilization, or when will we build our Dyson sphere? You just have to take historical energy use and plot it as a exponential graph, and you'll get to a date in the future when our energy use will match the total amount of energy that's falling on planet Earth. And a few thousand years later, our energy use will match all of the energy that is being emitted by the sun. Now, we don't know what it's going to be, and we don't know how we're going to use it, and we don't know any of that. But if the historical rise of energy can just be projected into the future. So is it like the same, is it the same technique? You're looking at the speed of migration, the speed of technology, and then just plotting that out into the future for what that may hold for expansion into the solar system.
It's not that simple. For example, we can say to estimate how we can achieve type 1 civilizations. We just cannot only focus on energy burning rate. Okay, for example, if we burn all the fossil fuel, we are going to destroy the atmosphere because the global warming, things like that. Then we dead before we reach type 1. So we need to balance, in our study, we need to balance this. How much fossil fuel we are going to burn, and how much we can increase energy consumption without destroying atmosphere. To do that, we take recommendations from IPCC, from international and climate agreement. So there's a limitations how much coal and fossil fuel you can burn. So we take that into the equation. And at the same time, how about the reusable energy and nuclear energy? How fast those new energy can be developed? So we also put that into the equation to estimate. So actually, in our prediction, you will see, and the fossil fuel consumption is going to be decreased, but the reusable new energy is going to increase. So balance all this out, we have our best estimate and how much energy consumption level we can reach that levels. And of course, if we burn all the fossil fuel, we can reach maybe in 20 years, 20 years, but we cannot do that. And very similar things when we estimate and how, what time we needed, the time frame for human exploration into space. We cannot just say, hey, we use the speed and of computer chips. We can do that. No, and we have to consider economic impact, how much money we have, and what is the economic speed of economic development speed. So we put that into the equation to have our best estimate. So this is our models is for.
Right. And sorry, another similar one that I've seen as well is how long it's going to take for humanity to utilize all the resources in the solar system. And
that's right. Yes.
Again, if you just sort of take the gross domestic product of the Earth, of planet Earth, and you take a reasonable GDP like 2%, and you just keep scaling that up into the future. Again, in a few hundred years, we are harvesting resources across the solar system. It's surprising how quickly compounding exponential increase dramatically changes what we do. Are those? I mean, it feels like those factors. How quickly we switch over from fossil fuels to renewable, whether or not we implement nuclear for baseload power. Those are important in the near term, but in the medium to far term, it's all just hazy. Like, you can't make any specific predictions about the technology that will be used. It's you just have to trust the exponential growth curve and figure that humanity will figure it out. As long as we can avoid the fossil fuel global warming great filter, then we're off to the races.
Right. Yes, you are absolutely right. Those kind of predictions is not certain is our best estimate, or something called educated estimate. Okay. And part of the reason we work on this is to encourage people to think, to discuss, and so to think about it. And so we are citizens of the Earth. And now, last year, actually, I saw a photograph taken by JPL and on the surface of the Mars. And it's a photograph of the Earth. You look at this photograph, it's a tiny dot surrounded by darkness. Okay, if you're on the Earth, you look at the Mars, it's tiny dot, and so it's actually very thought-provoking. If you look at this dot, everybody, you and me, we are on this tiny dot, and as I said, and the physics says right now we are trapped on this tiny dot with limited resources. Okay, now assuming if there's any alien beings, come to visit us, okay, tiny dot, okay, they observe us, I think their conclusion is very likely to be humans are very stupid. Why?
You may not be wrong.
Yes, and one thing they found is humans behave like children, okay, and not only individual behave like children, country to country behave like children, two countries are neighbors, okay, one country believes that, another country believes that, they fight. They cannot get along, they fight each other, and last month, not this month, this month, there's a military parade, in Russia, and maybe in October, there's military parade in China or something. You see those soldiers who step over the square, they carry weapons, and there's a trucks carry missiles. Those missiles carry nuclear bombs, and you see. Interesting thing is the people watch the parade, the audience, they feel proud. Wow, so powerful. Aliens don't understand why we feel proud, because we are watching weapons to kill ourselves. Mass destruction is not to kill animals, it's not for hunting, to kill ourselves. They feel proud. Such behavior tell us we are children. We are not grown up yet. We are not grown up yet. And it's very interesting. And when I submit a paper published, it's called Beacon in the Galaxy. We try to send a message in the deep space. At least we think about it. Although we don't have a plan. I got emails, all sorts of emails attack me, say, hey, you should not send this message, it's danger to us, things like that.
Yes.
That kind of thinking actually is human thinking, because humans are children. We fight each other. We think aliens fight each other. But I remember what Carl Sagan said years ago. If we discovered a message from the deep space, if somebody is visiting us, it's good news to us. Why? We learn they survived. That's lesson to us.
People always ask me that. If I could ask a question to an alien civilization, what would it be? And it would just be like, how did you do it?
How did you do it?
Yeah.
Yes. So one day in the future, if we are able to travel to the stars, it means we are grown up. We are not children anymore. We are in peace. And so right now, I don't see any light. We can do that. And so we just behave like children all the time. We're short-sighted.
So what does the math say for the expansion of humanity throughout the solar system over time?
Okay. And so let's say if we don't destroy ourselves.
Sure. Yeah, no, like everything's going to go fine. We're going to continue
in
on
the
into the
year,
future.
I think, in order to travel to the stars, approximately 200 to 300 years from now, we are able to do that, at least to Proxima B and Proxima Centauri. We should have the technology to do that. Now, and NASA actually had the plans to land astronaut on the moon again in 2028, onto the Mars again, and in 2038. Okay, so think about the Jupiter's moon. Probably that's doable in about 50 years from now.
Like humans to Jupiter's moons in about 50 years.
Yes, and it's all I say is doable. And based on the speed of technological advancement,
right?
And it is doable. So that's roughly the timelines are. So you think about the travel to the stars, and in 200 to 300 years, at least we can launch that mission, and it's doable. And assume we can survive that.
So I just want to understand, like, you're not thinking about specific technologies. You're not thinking about fusion rockets versus antimatter drives versus anything. Mm-hmm. What is the underlying I guess what is the math that you're using to kind of predict this, that Jupiter by 50 years, Saturn by whatever number, the outer planets, Uranus, Neptune, etc. What is the sort of explain where I'm kind of going with this, right? Like humans went to the moon in 1969 and set foot on the moon.
Right.
I would argue that they did that early, that they went to the moon by spending too much money, more than they could afford in the annual budget of the United States. They did it as a show of strength, as a show of military, as soldiers goose-stepping across the square, but also a feat of science and engineering and showing the capability of the United States. But now here we are in 2022, and going to the moon is achievable on a fraction of the budget, well within the capabilities of NASA, using technology off the shelf. All of this technology has been just constantly bringing the prices down, and going to the moon is very feasible now. If we had this conversation again and say we didn't go to the moon and we talked in 50 more years, going to the moon would be easy, be trivial, that for something would happen, the technology would come down. So I guess as we think about going to Mars, as we think about going to Jupiter, whatever, there is too soon. You're spending way too much money. It's too dangerous, too risky. There's entirely feasible, and then there's trivial. And what is the math that drives those too soon, doable, trivial?
Okay. And if we are not going to do it, if US is not going to do it, somebody's going to do it. Like China.
Yeah, I mean, there's probably 5 separate groups thinking about going to the moon this time.
No. Okay, so I give you a little background of its potential growth. Okay, and this is good things and bad things about that. Think about the life on the Earth. Okay, and Earth's about 4.5 billion years old. The first life appears maybe 3 billion years ago. Okay, the single cell. Okay. It took about 1 billion years to have a multi-cell. Okay, took about another 500 million years to have simple life in the oceans. Took about hundreds of millions of years, to have something come out from the ocean on the land. It is a mammal. Okay, and then you think about the human. Okay, our ancestors maybe 1 million years ago, but it took 1 million years for ancestors migrate from East Africa, and to other parts of the world very, very slowly. Okay. Now think about modern human. It's not more than 100,000 years ago. But written language start to appear maybe 5,000 years ago, maybe 10,000 years ago. Okay, at that time frame. Now, the language of mathematics probably happens only about 1,000 years ago. Okay, and so before that, they all philosophers. And our universe can be understood by mathematics. Without mathematics, we don't know, say the things like black holes, like cosmic expansion, things like that. Now, after that, there's a language it's called computer language. It's a binary. This happens probably 100 years ago, to the most. To the most. So you see the speed of development is accelerating. It's accelerating. You talked about artificial intelligence. It may happen. There's an AI had a similar IQ to us maybe in the next 10 years.
Yep.
Okay. So one of the mystery is acceleration. Something is accelerating. Do we accelerate to extinction? Do we accelerating into something? Now, in the math, if something is stable, okay, something is stable, you don't see any accelerating trend. If something is accelerating, it means something you are downfall. You are hit a cliff, maybe a slope. You are accelerating into something. So this is very thought-provoking. Are we face extinction, or are we face something for us become something? Now, okay, this is the general background. So, in terms of mathematics, you look at the historical data, you work out the formula. It's exponential growth for everything. Okay, and human advancement. Think about the technology, the speed of computer chips, and the speed of our development. There's accelerating curve. Of course, we don't know the future. Okay, but we can predict based on our current trend. This acceleration, technology development, economic development, human cultures. We can always predict. Okay, something is going to happen. When? Okay, we can have a rough estimate. So this is what is the mathematical thinking is behind.
Yes, but I guess I mean maybe I'm not sort of getting this across, but but there are underlying factors that are growing exponentially, and those factors in terms of technology getting faster, of energy use becoming greater, of et cetera. And I'll give you sort of another example and see if we can kind of triangulate on this. So I'm sure you're familiar with this idea of the weight calculation.
Yes, right.
Do you send a spacecraft, or do you wait for better technology and then send the spacecraft? Because nothing would be more embarrassing than to be on the spacecraft and watching the next generation fly past you in the faster spacecraft. And so when you calculate the amount of energy that it would just take to take mass from the Earth to Alpha Centauri or Proxima Centauri, and you consider it as, not too soon, not when you're spending half of the economy of the entire planet, you're spending a reasonable amount. Say you're spending 1% of GDP. Like there's a, and if you just wait 10 years, like if you're going to spend 50% in 2050, or sorry, 2500, and then you wait 10 years and 25, I don't even know how to say these numbers, 2510, now it's only 1% of GDP. And so if you just wait, then it makes more sense, and you can use that energy use. And I guess I just feel like in the paper that you did, the expansion of humanity throughout the solar system falls out, not because you're predicting a specific fusion drive. There are these underlying mathematical factors that are rising at an exponential rate, and they are and the date of humanity reaching Saturn falls out of this math. And I'm just wondering, what are the exponential growth curves that are feeding into this model that you are developing? And I'm specifically, I'd like to know about the solar system, and then we can talk about other star systems.
Okay, and so one factor is there's a few factors. One is the human population. the human population growth is you can see is more than exponential. And between 1800, humans population is below 1 billion. Below 1 billion for thousands of years. Okay, it's always stable. But after 2015, within 200 years, now we are more than 8 billion. and if you see that curve, okay, and of course it slowed down a little bit, but it's hard to see where to slow it down. Okay, now let's say if 1% of people think about 0.001% of people think about space exploration. Okay, this is already a lot.
Right.
And so this is already a lot. And also the economic expansion and also the speed of technology development. And so it's just no way to slow this things down. Okay. And so for that prediction, of course, you can think about medicine, government regulations, and maybe the impact of economics. So this kind of prediction is you can always make. And but I should say I'm currently working on another paper, and I haven't finished yet. And to simulate whether or not there's a dangers we can destroy ourselves. Okay, I mentioned the nuclear war. Okay. And the percentage of it's maybe it's very low. Okay, another factor may be asteroid hitting the Earth. Okay, between the Mars orbit and Jupiter's orbit, there's millions, hundreds of millions of asteroids. Okay, it's called asteroid belt, and Jupiter is moving around the sun, the Mars around the sun, so there's a gravitational perturbation and push and pull. So sooner or later, some of the asteroids maybe leave their stable orbit, moving close to us. And so you see in the news, and every now and then there's asteroids, skip by the Earth. Chances of hitting the Earth may be 0.0001%. Okay, it's low. And also pandemic, fortunately the current pandemic death rate is very low. Okay, but in the history, there was a pandemic death rate is very high. Fortunately, during that time we don't have air travel, so it's localized. How about the next pandemic? And we don't know. And also artificial intelligence. If 10 years later, 20 years later, the IQ of AI is higher than us,
Sure.
So my next paper is going to be to estimate. Okay, let's say we need another 200 years and 300 years, we can travel to the stars. But can we destroy ourselves? What is the possibility we can destroy ourselves before that? Okay,
right.
And using computer, you can estimate. You see the chances we destroy ourselves maybe is low, 0.001%. Let's say you buy a lottery ticket, the chances of a win is very low. But you buy the lottery ticket every day for millions of years, you're going to win. Okay. Yeah. So sooner or later we are going to kill ourselves. The question is when.
Sure. Yeah, so, and I totally understand the line of argument, right? That there are many existential threats that face humanity, from asteroid strikes to artificial intelligence to some script kiddie in a his Lil bio lab making viruses that can wipe out humanity. And I guess I got the impression from your paper that obviously there are plenty of you don't need to justify why we should go to space. This channel is all about that. And all of my audience is 100% on board with let's go to space. They want to know, we're not the people that you need to convince that this is important. You are preaching to the choir here. What is the reasonable rate that this happens? What is the
okay?
Let me try this again. I think people are shocked at the results of exponential growth that we saw with coronavirus. We see with all of these things that we instinctively are unable to appreciate what happens with exponential growth and how much it dramatically changes the future. And that whole idea, if you have you have a pond and you have some kind of lily pad that is growing across the pond, and on day 100, if it doubles every day, on day 100 it's full, and day 99 it's half full, and so you don't realize that suddenly the whole thing is covered in lily pads. And so this idea of exponential growth, that we're, as you say, we're thinking about nuclear war, and we're thinking about our daily, inflation. We're thinking about all these things day to day, but the underlying forces of exponential growth just continue on, and they will carry, again, assuming we dodge all of the scary things, there are these underlying forces, these underlying accelerating exponential forces that will carry us into places that make, in my opinion, traveling to Proxima Centauri inevitable. Not like it's something that we should try and figure out a way to do, that we will get to a place where someone goes, oh, you know what? No one's ever done it, so I'm just going to fly to Alpha Centauri because because it's relatively inexpensive, in the same way that we can now fly to Europe because it's relatively inexpensive. And I guess I'm trying to just understand that exponential growth that you're considering.
I'm considering is this, and it is, we need to think about right now. I think, go back to the question about great filters, Fermi paradox, and I think the great filter is us.
Mm-hmm.
We are the great filters of ourselves. We are heading towards that. And now look at this background you have on your background. There's thin layers of atmospheres are there. I talk about this tiny dot. We are not living on the center of this tiny dot. We are on the surface. It's very, very thin. Everybody living on, let's say, all the life we know in the universe, plus minus 1 kilometer on that. And we are destroying this atmosphere. We pollute it.
Yeah, you're watching. You've got the telescopes to see it happening.
Yes. So anyway, and now the underlying thought, the urgency is, and like Steve Hawking is thinking, we got to think about this, and we got to think about that. One, so whether or not we can survive, how long we can survive, how long we can avoid these great filters, I think it's the time to ask these questions.
Mm-hmm.
And so of course, those math models have uncertainties, and so we have limited data to the future, and so we just estimate the best we can do.
Yeah.
It's like before the rocket launch. We have limited amount of data. Whether or not we should push the button, to launch it, there's always a danger, maybe crash, but we have to do it. We have to do it. What is the likelihood to succeed, to survive?
Right. Yeah.
And
so, like, let's fast forward, say 100 years from now, 20. We'll go by the century. So what, assuming we avoid all of the great filter threats, it's the year 2100. How far do you anticipate humanity will have spread across the solar system?
Okay, in my view, that never happened, and for the mass migration of people talk about, Elon Musk talk about build a city on Mars. So a million people there, and I don't think it's going to happen. And it's not because of our technical capabilities. It's again back to the human behavior. There's this piece of land, that piece of land belong to who? That's always fine. And also, it's very expensive. Humans are very vulnerable. The Martian atmospheres, surface of the moon, and so it's dangerous to us. So that's why it's very expensive for us. I think in the future, it's easier for the robots to do that.
Mm-hmm.
Think about building a base of the moon. The current design is, and to manufacture all the parts on the surface of the Earth, then ship to the moon. The robots is going to do the assemblies to build a mother base first, Okay, then maybe human can move into the mother base once it's built.
Sure.
Then from the mother base, gradually the robots will come out to build the children's base. So that's what expansions are.
Sure.
Okay, and it's similar things to the Mars. So if I can guess, 100 years from now, there's populations of humans on the Mars, in the cities,
right,
on the Mars.
And like at this point, you've got robots that are manufacturing everything that we require to make it as habitable as possible.
Yeah, this is doable.
Yeah,
people, the vast majority of the people is still going to live on the Earth.
Mm-hmm.
Okay, if we can avoid climate change.
Yes, yeah. Again, we've avoided all those things. We did it. Where the aliens look at us and go, they're doing all right, because they avoided all those things. They no longer have wars. Everything is great, and now we are all of the good exponential growth curves are taking hold and things are moving. So within 100 years, we've got permanent habitation on, and the key is robots, right? The key is the robots. Yes, the robots.
Right.
So 200 years. Where do you think we are by 200 years?
Okay, 200 years, and now we need a breakthrough in physics, and it enable us to travel to the stars based on our current technology. Okay, because the speed of light is the limit. Even the star closest to us, Proxima Centauri, and 4.3 light years away, it still need more than 10,000 years to reach there.
Yes.
Based on our current rocket technology. Okay, so you can launch a robot missions, to travel to the stars, or you can launch an astronaut. But astronaut has to carry the wife, children, live there,
the water, the food.
So now I bet, we are going to have a breakthroughs in physics, and people and physicists are working hard. On the paper, it's not entirely unlikely we travel through the wormholes. Okay, and how to realize that we don't know yet. Okay,
I agree that a fundamental breakthrough in physics would help. It would bring reality in line with the science fiction fantasy that we've all been watching, Star Trek and Stargate and all of that kind of stuff. But even if a breakthrough in physics doesn't come about, our ability to spread from star to star is still possible within the laws of physics. You just need more time, more energy,
right?
Or I guess more energy. Okay. Like if you can harness the power of the star to accelerate your spacecraft, then maybe you need an extra 100 years to gather that much energy, right?
Right, but not only the energy, and again, it's a great filter in our human behavior. Now, the type 1 civilization, not only the energy level is 10 to the power 16, is type 1 civilization means we can consume that amount of energy, 10 to the power of 16, and also don't destroy the Earth.
Yes.
Okay, so we are in peace with the Earth.
Yeah, again, we did it. We made it. Everything's great.
Now,
yeah.
Type 2 civilization is we can harvest all the available energy in the solar system. We can not only live on the Earth, live on the Mars, the Moon, the Jupiter's moon. So we are in peace with the solar system. As long as our sun survive, we are survive. Type 3 civilization is we are in peace with the galaxy. We can travel across the stars, go to the galaxies. This need not only the energy consumption, probably we need breakthroughs in physics to make it easier. Otherwise, and I need to do another study to see if it's possible. Within current understanding of physics, let's say we can survive millions of years from now, and is it doable? and why we think about that is because one thing, the resources on the Earth is limited. Okay, And humans are very vulnerable. We need this atmosphere, this temperature to live, okay? And harsh environment and outside the Earth, even on the Mars. And so if we live on the Mars, in the end, we need to transform the atmosphere and things like that. Across the vast distance, I'm pretty sure the robots can do that. Okay, robots can do that millions of years down the road. Humans can survive that long travel, and I need to think about that.
We have thought. I mean, I guess humans have survived for millions of years,
right?
And so
right. Oh, yeah, you're absolutely right.
And there have been, and think about crocodiles. So species can live as long as they are hardy and, and in our case, it is in our hands.
It's always amazed me. 10 years ago, people talk about one trip to Mars, okay? No coming back.
Yeah.
We did this before. The people used to live in Africa. When they migrate to another continent, no way back. Even most recently, 18th centuries, Europeans come to North America. One trip, there's a one way. Okay, they live in North America, they develop, and so so people can do that. A one-way trip to the stars.
Right.
What I'm saying is this: the lifetime of humans is limited, say to 100 years. And our current technology, current physics says you need quite a few generations,
Yes.
And in some transportations, in order to reach there.
But it feels like fundamentally like here on Earth, sure, when humanity was leaving Africa and moving to other continents, the places they were going still had breathable air, water you could drink, animals you could hunt, plants that you could harvest. You just had to learn which ones were poisonous and which ones were dangerous.
Yeah.
But going to the moon, going to Mars, going to other star systems, they are going to be fundamentally inhospitable to human life. That it's only our technology that will make these places habitable for us, either in closed environments where we simulate everything or through terraforming. So is the indication that this is starting to happen when our robots get good at preparing places for us to survive?
Okay. Think about the Europeans coming from North America. The trip takes about months. Okay. And humans itself cannot do that. You need ships. Okay, human need to build equipment, ship, to do that. Again, it's months. Okay, and travel to the moon and Mars. And yes, we need to build ship. It's taking about not months, maybe a year. Okay, now travel to the stars. If humans in that, we need to build a ship. Now, unfortunately, the time scale is huge. It's 1,000 years. So that said, and it's very difficult for us to survive that long because the limitation of our biology. So that is why we think robots is our children. Okay, they are going to do that.
Now I would propose to you that you're not trusting in the math. Like if you take, let's say you have a spaceship that carries 100 settlers on a spaceship and you want to take it to Proxima Centauri and you want to be able to take everything they need to be able to set up, bring their robots, or maybe the robots have already gone. And you want them to be able to go within their lifetime. Say you want them to be able to make the journey at 50% the speed of light. Then that is there is a mathematical number that tells you the amount of energy that you're going to require to be able to make that journey at the speed that you want to be able to make it. It's a lot. It's an incomprehensible amount of energy to move a 10-ton spaceship from Earth to Proxima Centauri within 2 years. But it is a number. And if you then take that number and you compare it against the growth of energy use by humanity, those numbers will cross at some point. That at some point in the future, it's maybe it'll be 400
now I
years,
get it.
maybe it'll be 800 years. There will be a number when that number does cross, and so it's like as long as you trust in them. Again, assuming we avoid all of the dangers, and we trust in the growth of that we trust in exponential growth, then all of these things that we can imagine will almost inevitably happen. It's just a matter of obviously it's details.
Okay.
Right.
I get it.
But,
okay.
So, yeah.
And okay, now I get it. I actually have a student to work on that, and to work on you said to work on whether or not it's possible for humanity to reach type 2 civilizations. It's going to be mathematical computer simulations to do that. Okay. That including the factors you just said. Okay. And I think if we reach type 2 civilizations, okay, that amount of energy you are talking about is no problem.
Yeah.
Okay. And we can do that. And we haven't finished the simulations. Now, if you talk to me again sometime next year, this time, I should have the result. And it need a detailed simulation, not only calculate amount of energy available on the Earth, but also taking consider human migration to the solar systems. Okay, and we can settle down to the solar systems. And my personal will tells me if the computer simulation is correct, it is doable. I don't have the timeline yet because we haven't finished the simulations. And so my gut feeling is it will take close to 1,000 years.
Yeah. But again, like 1,000 years, when you think about like humanity's been around for 1 million years.
Doable.
And 1,000 years ago, we were in the Middle Ages, and life was short, brutish, and cruel. And 1,000 years from now is a blink of the eye. And yet, if you chart humanity's growth forward, we will in 1,000 years ish, we will be harvesting all of the power from our star. And we will be trivially sending spacecraft to other star systems in the kinds of short time frames that we all would like to see in our science fiction. And I think that doing it to, and I think, so I feel like the modern space exploration movement is sort of really focused on doing it too soon, before that energy use, before the robots are ready.
I agree.
And it's the robots that will, when we have our self-replicating robots that are out there tearing asteroids apart, building wonderful habitable space stations for us to survive on, that's when we know that this is coming true. And but trying to go and live on Mars and hide in a tunnel and try to grow potatoes in your own poop is gonna be suffering. It's gonna be worse than living in Antarctica times 1,000.
Right. And I agree. And I think within 1,000 years we are able to do that, to travel to the stars. And it's going to happen anyway. Nobody can stop that.
Yeah.
Because there's a pressures on us. Not only the pressure on the population, pressures of resources, and most importantly, and our inspiration to go out. It's always, life. One of the definition of think about the virus. Okay, they spread, and this kind of, you call it inspiration. Human is the same. We want to spread, and no matter what, it is going to happen. Giving 1,000 years, and of course, I myself, maybe Steve Hawking's influence, think too much about, can we survive that long?
That's
yes,
yeah,
right.
Of course, and we always need, but it's like we always need to be worried about the risks that we face. But we also but then we risk. What if things turn out well? right?
Yeah.
We don't think
Yeah.
about the what if everything
So-
goes great.
Yes. So you are right. Actually, you just hit button of my inspiration to work on this project, because I bet you have. We have positive passions to the future. That's why we are doing it. And I think in the positive side, and humanity will sooner or later to travel to the stars. And our children's children, and their grandchildren's grandchildren, they are going to do it.
Yeah. It's funny. I have this conversation with people from some NASA and other places about say Starship, and right now we're in in the area where Starship hasn't launched and it hasn't proven that it can be a fully reusable 2-stage rocket. But if it works, then you've got a rocket capable of lifting 150 tons to low Earth orbit with a 9-meter fairing for just a few $1 million per launch. That it would change everything about the way missions are designed and built. And yet everyone is so concerned but that it's not going to work that they don't think about, like, what if it does? Like, how do you, like you're going to be busy coming up with a new atmospheric modeling space satellite that can be 150 tons and fit within a 9-meter fairing. That is a complex job, and there needs to be some time spent to think about it. And I think it's just the same thing.
I fully agree. And let me add to that on that. And my father told me, when my father is a kid, 1930s, my grandfather told my father, hey, and when you grown up, they're going to be something like not train station, it's something called airport. You go to the airport, bring your luggage, you can fly to any other cities around the world. My father said, really? Nobody believed that. I'm going to tell my daughter, when you grown up, they're going to be a spaceport. You take your luggage to go to the spaceport, and then there's a rocket to take you any place in the solar system. I think that's going to happen. If it's not my daughter's generation, my daughter's granddaughter's generation. Yes, it is going to happen.
And it feels to me like you can predict these things mathematically. You don't have to say how. And she'll, and your daughter may go like, how? And you're like, I don't know. But the math says it'll happen. That the energy use will grow, our capabilities will grow, and you will be able to go to the spaceport and hop on your space plane, and away you go. And
you are absolutely right. The math is based on data, based on current understandings. If you take all those data to do the simulation, it's going to happen. And so because scientific research, you have to base on the facts, not something come from the mind. You take all the facts, all the historical data, you put in the model, you do the simulations. Well, you come up with a result. Of course, you can also to analyze the uncertainties, the range of your predictions. That's doable. And so based on that, the science and math put together, it tells us it's going to happen.
And I think that we've seen this go the other way. Like at the very beginning of the pandemic with COVID, scientists were saying this could kill 1 million plus people in the United States. This could kill tens of millions of people around the world. This is really serious. And nobody thought that was possible. But the math, the exponential math underlying the whole thing was telling you how this would end. And we are still following along the math, the curve of the math, with kind of brutal predictability.
This is scientific prediction. So prediction has to be based on the data, not from the mind again. People think, that's not true. You based on the data. That's the real predictions. So answer your questions at the beginning. Based on the data we have, humans are going to land on Mars, move to the Jupiter's moon within about 50 years from now. Based on the data, we are able to travel. Whether or not we can reach that to Proxima Centauri, Proxima B, to say 200 to 300 years from now. Now, whether or not we can live on the stars should be about 1,000 years from now.
Amazing.
Okay. So if we trust the data again, nobody believes that. Even my boss,
I do.
don't believe that.
Yeah, I do. I trust the data.
Yeah. So it's going to happen.
Yeah.
And so I'm going to tell my granddaughters, at least tell my daughters, that's going to happen.
Yeah. Yeah.
Yeah.
And on that note, maybe later on, another time, we'll talk about all the horrible things that we have to avoid, because I have opinions on that too. But every now and then, I think it's fun to speculate and hope for the best, and even as I said earlier, that you need to be prepared for the best, because even the best can be an enormous challenge that is going to keep you really busy. Right? What if you succeed is a question that I think people rarely ask, and it is sometimes really important to ask yourself. Well, Dr. Jiang, it's been absolutely fascinating talking to you. Super fun. What is the best way to keep track of the work that you're doing?
Okay, so the best way is to check my papers. Okay?
Yes.
And whenever I publish something, and read that. If you have any question, you just call me.
Fantastic.
And I'm going to answer that.
Wonderful. Well, thank you so much, and good luck with all of your research, and I'll see you on Proxima Centauri.
Okay, thank you so much. Okay,
all right.
Thank you.
All right.
Okay, see you there too. Yeah, bye-bye now.
Bye-bye.